CMSA. It's a pleasure to welcome everybody that's here in Bonn and online. I hope you'll find out more about the CMSA. I'm not going to say much about it now, but there's a newsletter for those of you here. It's lying around, it's online, there's a film as well, so you can see the kinds of activities we do. But without further ado, the next set of lectures is by Mike Hopkins, who will talk about lattice models and topological field theory.
Thank you, Dan. Is this on now? Everyone can hear? True on Zoom world. So I want to talk about, as the title suggests, a connection between these Hamiltonian lattice systems, like we heard about in Bruno's talk earlier today, and some more topological aspects connecting to topological quantum field theories. So a lot of my interest in this, or my kind of obsessive interest in this, came from interactions with Alexei Kitaev and a group of other people at the Aspen Center for Physics, starting about 10 years ago. And Alexei made some conjectures then, and I can't remember what kind of conjectures they are. So in Aspen, you're sitting around listening to a talk or whispering to each other and saying things that maybe are not meant to be taken too seriously, or you're hiking and you're standing on top of a mountain at 15,000 feet, yelling to the world that the things that you feel are truths inside of you are true for all of humankind. And I don't know I can't remember which one of these was the kind of statement that Alexei made when he made this conjecture. To me, it sort of felt like the true for all humankind kind, but I just ran into Alexei earlier, and he's also going to talk about these conjectures, and anyway, he can decide what kind of statement it was. So, all right. So let me get started. So I need to have some notes up. So in the last talk, we learned a little bit about this setup where you have a big space and a bunch of sites in it, some kind of discrete set of points inside a big metric space. So I want to think of this ambient space as some kind of a metric space. And this collection of points is like Rn. And this collection of points is some kind of lattice in Rn. And in a way, everything only depends just on this collection of points as a metric space, but it helps to think of it embedded in Rn or other spaces. And then a typical, I'm not going to go into very many details about this, but you have some kind of, you have for each L in this lattice, so I'll call this collection of points here L. For each site, you have a Hilbert space, sort of HL. These form some kind of Hilbert space. And these form some kind of a vector bundle, if you want, over L, but I'm going to assume that the dimension is constant, or at least bounded. All right, and then the physics, just very crudely, that you model. I mean, as we learned in the last lecture, we study the physics on this by algebras of local operators and the apparatus of algebraic quantum field theory there. What I want to just pull away from that is that you have a Hamiltonian, which is a Hermitian operator acting roughly on, I'll put this in quotes, on the tensor product of all the HLs. So H is a Hermitian operator, and we want to look at the collection of these for which H has a spectral gap. So let me give a name for that. Let me just use the symbol X, either for this metric space or the ambient one. I'm going to write Lx for the collection of gapped Hamiltonian systems on that. So you have to forgive me for not having really solid foundations here. And in a way, I think my justification of that, well, the fact is I don't really know them very well, but I think there's some justification in being a little agnostic about this, because Alexei's conjecture has to do with a more or less purely topological description of kind of the topology of these objects. And there's a lot of tuning of the definitions to make that work out, and both on the topology side and on this side. So I'm going to be a little bit vague and kind of proceed with pictures largely. So this is some collection of all of these systems on X. So the toric code would be a point in this Lx when this is the plane and things like that. And so the idea is to try and describe kind of the large scale structure of this Lx, or just, what are the topological, can we make this into some kind of a space, and what are the topological invariants of this? All right, so I'm gonna kind of beeline down to Alexei's conjecture, and then step back and talk about tuning the two sides, the topological and the analytical sides, and trying to tune them to each other. So you have to imagine that that you can move these points around, or you can even add new points, as long as everything is done in a bounded region. So you're allowed to make local changes in this. And in that sense, you want to think of this as kind of forming a topological space with local modifications. There's also an operation from L of x cos Lx to L of x, which just takes, it takes two systems. And again, I'm sorry, I'm allowed to add new points sometimes. And I just combine the list of Hilbert spaces, and so the tensor product becomes the tensor product and the Hamiltonians. So let me just say this sends H1, H2 to H1, tensor the identity, plus the identity tensor H2. So this is H1 is acting on some, HI is acting on some big tensor product of need another I here. What do I call this? HL. So these might be slightly different lattices inside. HI is some action on this, and then the H is tensor here. So this thing here, this combined Hamiltonian acts on the tensor product of the H1 L1s with the tensor product of the H2. Okay, so that's just, this is just a heuristic, really. These have to be local operators, as described in the last lecture. But this is a way of combining two systems called stacking. And okay, and then finally, there's I want to imagine there's a trivial system where each HLI is just the complex numbers with no, and the Hamiltonian is 0. And then in principle, that doesn't change. That acts as an identity. So I say in principle because everything is kind of up to deformation. I might have added new points in here, and that's merely canonically isomorphic to L, my original system, but maybe not the same. All right, and so oh, I didn't, and so you're supposed to, this condition of it being gapped is important. So these are Hermitian operators. They have real eigenvalues, and you're supposed to imagine that there's a lowest energy state, and then there's a gap between that and the next one up. All right, and so finally we get to an important definition that's a little hard to verify a priori given one of these systems. So definition, a lattice model H in L of X is invertible if there exists an H prime in L of X, and such that H tensor H primed is equivalent to, sorry, this was supposed to be something like this. I didn't give this a good name. I'm just, what's that? That's okay. Okay, I'm sorry.
It was a square.
Square? Oh,
Square cross.
okay, that's good. Thank you. Yeah. Oh, but that's better. Thank you. Thank you. I needed you when I was preparing my notes. Thanks. Right. So that's equivalent to the trivial system. And so these, there's a lot packed into these, and I'm sorry I'm starting at a kind of maybe a not a very precise place to start, but I want to focus hard. Anyway, I want to get this connection up. So yeah,
are you assuming that these discrete subspaces are quasi-symmetric?
Yeah, probably so. Yeah. I think that's probably a good idea. Or I'm remembering. I'm actually kind of remembering X and then thinking of this site. Just choosing lattices living on X. But yeah. Okay, so those are invertible, and then there's a theorem that Kitaev proves, which I think you'll hopefully hear a lot more about later this week, which is that, so a theorem that these so let me give a name for the invertible ones. Okay, so let's let, I'm going to let K of X let these be the subset of invertible lattice models. All right. And so Alexi's theorem is that K of X, K of Rn plus 1 is the loop space K of Rn. So the K of Rn's form a spectrum in the sense of algebraic topology. So a spectrum you can think of as a cohomology theory. And then there's a question, what spectrum is this? And okay, so the conjecture about what that is this conjecture that was either whispered in the back of a classroom or shouted from a mountaintop And I want to try to, it has a very beautiful answer. It's the guess for what this is. It's a very beautiful object, and it's very, from the point of view of algebraic topology. And my whole series of talks is going to be how we might, what mysteries that raises about both sides, and how we can try to understand how you might relate these. Okay, so that was very brief. I'll come back and talk a lot more about lattice models and things in my last two lectures. My first two are going to focus more on the topological side of things. All right, so. Okay. Now, I need to say a little bit about spectra. Okay, so let me just, I'm going to take a minute and, in the sense of topology, so there's a lot of ways of introducing these. I'm going to mention it in the most convenient way that connects to this. So first, we say that a functor, suppose we have a functor here from spaces to abelian groups. So this is a cohomology theory is a functor like this, which is contravariant. Functor like this from spaces to abelian groups. Contravariant, and the most important thing is that it satisfies exactness, meaning that if X is U union V, then there's an exact sequence that goes from En of X, En of U plus En of V, that's the restriction, En of U intersect V, and then that connects around to En plus 1 of, I'm going to do this, En plus 1 of X, like that. All right, so this is an exact sequence, the Meyer-Viatora sequence, and it's an expression that E is accumulated, this group is accumulated from local data in X. And there's a theorem about this that when you have this, there's a theorem called Brown representability, which says that for such an E, so any such E is representable. So there's a space E upper N for every N. This is supposed to be an underline, and E upper N, En of X is homotopy classes of maps from X into this space E upper N. And if you play around with this sequence, when X is the disk, is an N sphere covered by two disks, you find that these spaces En have the property that En is the loop space of En plus 1, and that's meant to that's the sense in which, so such an E is called a spectrum, a collection of spaces like this. So a collection of these ENs and an isomorphism of En with the loops on En plus 1, that data is a spectrum in the sense of algebraic topology. Okay, so spectra represent cohomology theories. And okay, so now I want to go back, and for a reason I'll explain in a minute, I want to look at the spectrum that Kitaev writes down, but I want to index it in a funny way. So just to make sure I don't do it in two different funny ways, I'm going to define my spectrum K by saying its nth space is the space K of R n minus one. Oops, I think I did that right. Yeah, okay. So, all right, so I'm right, so this is, so, yes, I'm just shifting this index by one. And now the question is, what do we know about this Kn? Okay, so let's take,
So there's no K0?
yeah, there is a K0, there's even a K negative 100, but, okay, so I should say n bigger than or equal to 1, and then I'll define Km in general to be the loop space of Km plus 1. Okay, so there's probably some logic way we could, do something about the lattice models over the empty set and deduce this, but I don't know. Yeah, well, I'll just take this to be the definition.
It seems like the numbers go different because there's K Rn plus 1 is the loop space of the one.
Oh, yeah, that's, thank you. Yeah. This is not Alexi's theorem. Sorry about that. Thank you. Okay, so let's do a really simple example. Let's look at R0, which is just one point, and ask that what's this space L of R0? Okay, so now our Hilbert space is just some C is some. So I actually didn't tell you, but I'm thinking of Z2 graded vector spaces, so super vector spaces, and our L of R0 is we've got some super vector space C. We're looking at some. It's a collect. We have some C, P, Q, and some Hamiltonian acting on that with a gap in its spectrum. So if you have an operator and you've got some spectral gap, you can spectrally flatten it. You can just by a natural continuous deformation collapse the spectrum into a zero eigenspace and an eigenspace with value 1. That's called spectrally flattening. And then the only information that's left is this subspace. So this thing is homotopy equivalent to some disjoint union of Grassmannians of different subspaces of C, P, Q. It's a disjoint union over different Grassmannians, and then we have to allow P and Q to change. And if I made more precise definitions, we would have seen that we're allowed to stack systems on this, and so the P and Q could go to infinity. So in the end, it tells you that K of R0, that's just the one-dimensional. So to be invertible, all the Hilbert spaces have to be one-dimensional, the ground states, and so this just becomes the projective space of graded lines, and so this just becomes the collection of superlines. Or superlines. And that has the homotopy type of Z2, that's the grading, across CP infinity, which is the space of lines. All right, and that's the space I called K1. So K1, and this is just Z2 across CP infinity. And what's K? So to get back to Ezra's conveniently timed question, what is K0? So K0 is the loop space of that, which is homotopy equivalent to the circle, or maybe prosaically, it's also homotopy equivalent to the unit complex numbers. Okay, so that may or may not, depending on what you think about cohomology theories, this may or may not help you. But it turns out in topology, there's a kind of universal cohomology theory with this property. And so whatever this Kitaev spectrum turns out to be, it'll be related to the universal spectrum with this property. So the first thing I really want to introduce from topology is something called the Anderson dual, or sort of Anderson and what topologists call Brown combinates. Dual spectra. Okay. So I'm also going to do something that it's a little sloppy, but sometimes it's helpful to think of this as having the discrete topology, and sometimes it's helpful to think of it as having the continuous topology. And it's just something to really tune all these things, to tune this with the lattice model system and to tune it with topology. I want to be a little agnostic about this as I move along. I'll explain the two ways of looking at it. So Brown combinates duality has to do with when I think of this as having the continuous topology, the discrete topology, and Anderson duality has to do with when I think of that as having the continuous topology. But I'm going to be a little bit agnostic as I talk about that. Okay, so how does this work? So suppose I have a spectrum E. And remember that corresponds to a collection of spaces, En, and isomorphisms or homotopy equivalences of the loops on En plus 1 with En. And so the En has values on a sphere, right? So we write pi n of E to be the cohomology of a point. So that winds up being E0 of Sn. And that's good for n greater than or equal to 0. But by the suspension isomorphism, that's the same as E n plus k of Sk for any k. Okay, so for any k. And then if I take k sufficiently large, we can define pi n of E to be E n plus k, to be homotopy classes of maps from Sk into E n plus k. Sorry, my notation's a little bit off. Okay, we can define pi n of that E to be that for k sufficiently large. All right, and this is something that's exact. Okay. So let me think how I want to do this. So given an E, I didn't explain enough. All right, I'm just gonna declare something. So So C star with the discrete topology, that is, that's an injective abelian group. So if I have a cohomology theory, E, I'm sorry, I got myself into a corner here. So I'm just going to have to put up a definition that doesn't. So every cohomology theory has a companion homology theory. So if E is a spectrum, there's also a homology theory, E lower n of x, and that's defined. So this definition, if you've never seen it before, looks probably a little bit alarming. That's the limit as k goes to infinity of pi n plus k of en ek smashed x, where the smash product of pointed spaces is that's ek cross x mod the base point cross x and ek cross the base point. So I apologize. This is the companion homology theory. And if you've never seen this before, this is a little bit alarming, but I'll just tell you that in the case of ordinary homology and cohomology, in the case of ordinary cohomology, these E's are the Eilenberg-MacLane spaces, and this was a very surprising definition or recognition of homology that was discovered by George Whitehead in the 1970s. There's always a companion homology theory. Yeah.
In the definition, in the definition on the top, do you use cohomology, right?
I used cohomology here.
Yeah, and shouldn't it be minus n plus k? I mean, in this formula. But
Yeah, k minus n. Is that, now you got me mixed up.
No, it's about spheres.
I'm sorry. Yeah, sorry. Sorry, yes, yeah, thank you.
Sorry, it's the first line of definition because it's a pi n of a whole spectrum
That's pi n, yeah.
of E lower bar. Have we defined E lower bar?
E, yeah. Pi n of E, I think what I meant to say, pi n of E is pi n of E lower bar 0, which is also pi n plus k of E lower bar upper k. Now you're making me wonder if my sign is wrong. Oh, I see. This is what I should have said. Sorry about that. Okay, sorry. All right. Okay, so C star is an injective abelian group. So if I have a spectrum E, then I can define a new spectrum I'll call I of E by saying that the value of I of E on X is homomorphisms from, so I upper E 0 of X is homomorphisms from E lower 0 of X into C star. So I take all the exact sequences I have in homology and I just hom them into C star and get a bunch of exact sequences in cohomology. And by replacing X by a suspension, I get the value for all the E upper ends, but there's a sign error I'll make, and I'll clarify that when I come down and do a calculation. So sometimes we write this as I C star of X of E, and this is something called the Brown Kamenetz dual. Of E. All right, so I don't know. Okay. All right. Well, let's take an example. I'm going to let E be the sphere spectrum. So the sphere spectrum is defined by saying that the E homology of X is the kth stable homotopy group of X, which is the limit as n goes to infinity of pi n plus k of the n-fold suspension of X. So let me just call that with the symbol S. And I want to think about the spectrum IC star, which will just by definition be IC star of the sphere spectrum. So if you go through my formal definitions, so this represents this functor. So I of E is maps of spectra from E into I C star. And let's look at what the homotopy groups of I C star are. So pi n of I star is homotopy classes of maps from Sn into I C star, which is Hom pi 0 stable of Sn into C star. So the homotopy groups of IC star are the character groups of the homotopy groups of spheres. And so this number, I'm just going to tell you how the signs work out so that pi I of IC star is 0 for I greater than 0. Pi 0 of IC star is the character group of the integers. Pi -1 of IC star is Hom pi 1 of the sphere into C star, which is Z mod 2. And I get only in negative groups, I get the character groups of the homotopy groups of spheres. So if I knew all of them, I could write them all down, except just like for now, I don't have very much room. And so they go Z2, Z2, Z mod 24, and then there isn't enough room to tell you all the rest of it. Okay, so that's something. And more generally, for any spectrum E, this follows formally from the things I've told you for any E. Homotopy classes of maps from E into IC star is Hom pi 0 E into C cross. Okay, now that's a lot of formalism, and you might wonder, how does that connect to what Alexei was talking about? How does that connect to his conjecture? Well, let's look at the spaces that that live in this spectrum. Okay, so maybe I should say one other thing. There's a spectrum IZ, which is defined by a fiber sequence that goes IC. And IC, that's the thing So that's also injective. And then this map is the map from C to C star that'll just be given by e to the 2 pi I of whatever. And so IZ is defined by the fiber of that. And what's important for us is there's this connecting map to the suspension of IZ. All right, and this is the difference between giving this the discrete topology. If I think of C as having the continuous topology, that's the same as making this contractible, and giving this the continuous topology makes this an equivalence. All right, but I want to look at this I want to look at the space, the zero space of this. Okay, so the zero space of that. So what property does that have? Pi zero of that is C star, and it's a space, so there's no negative homotopy groups, and all the positive homotopy groups are zero. So pi I is zero for I not equal to C star. So the zero space of this is just C cross, and the zero space of this that's C cross with the continuous topology, or if you want, the circle. Okay. So let me just rewrite something that I had on the board. I think it's even still, oh, it's just over here. So I'll just walk over here and point. So for any E, homotopy classes of maps from E into this spectrum is just given by Hom of pi 0 of E into C cross. So let's go back to this Kitaev spectrum. And I think the way I worked out that the one space of that we decided was C cross. Or that I said was the zero space. Yes. Right, the zero space. The one space was the group of graded lines, and if I loop it down, I get C cross, which I can think of as given the discrete topology, or if I'm a little more careful, I can think of it as having the continuous topology. So there's the identity map from pi 0 of the Kitaev spectrum into C cross, and that corresponds to a map of spectra by this from the Kitaev spectrum to IC cross, or maybe to the suspension of IZ, depending on which we're talking about. And I introduced a term, and I should have defined it. So the Brown-Kamenetz dual in topology, the Brown-Kamenetz dual or Pontryagin dual of E is the spectrum of maps from E into IC cross, and the Anderson dual is maps from E into IZ. So these are related to each other, and I've been vague about the distinction between them. But the main point here was just on universal grounds, there's this spectrum in topology, and the Kitaev theory canonically maps to that spectrum. And so you might think the conjecture is that this is an equivalence. And that's not quite right. That doesn't work. This Kitaev spectrum also only has negative homotopy groups. And as you go, it looks good when you compute pi -1, it's an isomorphism, but by the time you get down to pi -3, things start to look wrong. So there's some modification needs to take place. Okay. All right, so I want to just keep pushing this formulation a little bit. So spectra themselves. When I have a spectrum E, I've said it's this collection of spaces En and isomorphisms of En with the loop space of En plus one. But this hides a little bit of something. It kind of hides a choice. This En is really, you should think of, so there's a slightly more general way to say this. You can think of this En as EV, where V is an n-dimensional vector space. And maybe even a subspace of some fixed big Hilbert space. And the reason I could do that is I can think of, I could define EK plus, say this. I want to say that, did this backwards again. Let me just say that you can do this. All right. I just, if I remember that, you know, E0 is loops n En, I could also take maps from the 1-point compactification of some vector space into E. Let me say that way. I'm sorry. I just, I think I'm running out of time. I want to, I don't want to get backed into a corner that makes me have to explain a lot of other stuff. So I could look at this space, maps from V into En, where V is just some n-dimensional vector space. Say it this way. All right, V is just an n-dimensional vector space, and SV means the 1-point compactification of V. Okay. And so if I take V to be Rn, I get the original E0. If I don't, I get something else. And so there's a few ways we can package this information. This has an action of On on it, because there's an action of On Rn. And so E0 has an action of On on it for every n. So in fact, E0 has an action of O on it, for O is the infinite orthogonal. All right, and in that, in turn, tells me there's actually an action of O on all of E, or any spectrum E. So the theory of spectra, if you want, has an action of the orthogonal group on it. And what Alexei conjectured is that the map from K into I C cross, that actually factors, that actually is fixed, not under the action of the orthogonal group, but under the action of the spin group. Okay, so there's a conjecture that this map lifts to the invariance under the spin group, and it's an equivalence. So there's two parts that exists, and the second part is this map is an equivalence. Okay, so I want to say this. So this sounds a little bit not very useful, but I want to point out that this is something, I want to describe this. Oh, I've got 10 minutes. That's just right. I want to describe that in terms of something that we understand. So I C star, this the fixed points under the action of spin, that's the same as the Anderson dual, the same as the spectrum of maps from spin boardism spectrum into IC cross. So that's the Brown-Kamenetz dual of spin boardism. I think I won't explain why but maybe it's at least plausible. This is the orbits of the spin group acting on something, and I'm mapping out of it. And there's something you have to check. to check that these group actions correspond. So another way of saying Kitaev's conjecture is that the spectrum built out of these gapped Hamiltonian lattice systems is equivalent to the Anderson or Brown-Kamenetz dual. In borders. Okay. Now, why is it so? All right. So this conjecture has just really fascinated me for a long time, and I've really I find this a very compelling question. This is an object, as we'll see. You can really understand this side completely. You could compute all of its homotopy groups. We understand this completely as a cohomology theory, and then that would in return give us a lot of information about the sort of topological data inherent in looking at the aggregate of all these gapped Hamiltonian lattice systems. And I just want to say a little bit about where I'm going to go with this. So I'll do a little bit more with this stable homotopy theory next time. But what I really want to do is explain a better connection between topological quantum field theories and this purely topological side. But even when you do all of that, there's a mystery about how you can see this spin invariance. It's a mystery from the topological side, and it reflects something that's present on the lattice model side. So I'll just say something. So the spin invariance from the Kitaev spectrum to IC cross, the spin invariance corresponds to something on the lattice side. So it corresponds to unitarity. In other words, the fact, so there, if I'm within the broad context of topological quantum field theories, it corresponds to them having an extra property, which is unitarity. That's the fact that the Hamiltonian was a Hermitian operator. So that unitarity, or in the language of topological quantum field theories, this is reflection positivity. And it corresponds to something that I don't know how to justify even in this language of lattice systems at all, which is an emergent Lorentz symmetry. So I'll say in the next lectures, I'll say more about topology. I won't be so. I don't think I'll do as much abstract stable homotopy theory, except I want to introduce you to a little bit about why this side is something we can understand so completely. But you're supposed to, on this side, imagine that you're not looking at some single lattice system, but it's written, like if you draw like a picture of the toric code, you've got this square lattice with these sites on all the edges, but you're allowed to zoom out, right? It looks the same as you zoom in or out. And so what you're really supposed to be imagining you're looking at here is some renormalization or some IR limit of kind of a physical systems which has emergent structures. So this SV thing here, it tells you that if this is in dimension n, so I'm looking at the n plus first space, at least the ON action, that's just the ON action on this ambient Euclidean space. There emerges a higher, an action of all of O on this space of phases that's largely a consequence of reflection positivity, but it's hard to see from the point of view of lattice models. But the fact that the spin group is supposed to be acting trivially, this Wick-rotated version of Lorentz symmetry, that's a mystery to me, even from the lattice model. So I do have a question, I'm sorry.
Actually, I have questions on this emergent Lorentz symmetry, because I mean, maybe I understand it wrongly, but from the beginning, with the lattice model, that's not relativistic. So
Yeah.
why is it not something like Galilean symmetry? So
Yeah.
where does the relativity aspect?
Yeah, you know,
mean-
I made this a little bit imprecise. Yeah, maybe it, I mean, I was thinking that the time direction is still, right, that's not Wick rotated when you talk about a
Okay.
Hamiltonian
Okay.
lattice system, right?
So
So I think it means, I think it's supposed to mean Lorentzian in that case, but I'm sorry, I can't, yeah.
Usually the spin structure are associated with the fermion. I want to make sure here, when you talk about the spin, you're talking about bosonic lattice system, no fermion involved.
The spin, by spin, I mean, yeah, sorry, that's a ambiguity, right? I don't mean spins in the sense of bosonic spins. I mean fermionic. I mean, yeah, the system.
I wonder what the spin is the spin structure, you're lifting O to apple covering.
Yeah, yeah.
But usually that structure appears when we talk about fermionic system, it's usually. But here, I want to make sure you really talk about bosonic lattice system and you still
No, we're
require.
talking about these were Z2 graded Hilbert spaces at every point. And I had Z2 graded lines. Yeah, so I really mean fermionic system.
So that means we don't think of bosonic vertical topological order. Then maybe this factor through spin is not required.
If it's bosonic, it's supposed to factor through the SO invariance. And that, yeah.
So that's okay.
So that's even, right. Sorry, this went this way, and then it factors through the SO invariance, which is even finer.
So this part specifies the study bosonic system or fermionic system.
Yeah,
We'll have a-
yeah. But again, it's hard to see that. And so one of the things I want to do, this is something you can tune. You can look on the topology side. Anyway, what I want to do in this series of lectures is explain some models, explain how this connects to topological quantum field theories, and just identify from at least the topological quantum field theory side what structures one might hope correspond to this emergent Lorentz symmetry. Maybe I'll just, in the 1 minute remaining, I'll say more about this later. You're not supposed to really think of an isolated lattice model. You're supposed to think, as I said, of something that's getting, you're either zooming out or the sites are getting finer and finer, and you're going to some kind of IR limit. And you can express the Lorentz symmetry or the spin symmetry by saying that once I have one of these phases or systems on Rn, I have a way of putting it on any spin manifold. And I'll come back to that later. I think I'll just come back to that later, but I just wanted to, I think I have a lot more to say about what this emergent symmetry might mean, but I'm at time, so I'll stop here. Thank you.